Integrating HumanIK in a game engine is pretty easy, and this is what I'm going to prove in this presentation. So what you are going to learn now is how to integrate HumanIK in your game and how to get some nice IK very easily by just writing a few lines of code. Let's begin by reviewing the pieces of software we start with. MotionBuilder is going to be useful for prototyping your IK. You can use HumanIK without knowing anything about MotionBuilder, but it is much easier to start working inside MotionBuilder instead of directly writing C++ code. The second piece of software you need is a HumanIK package. And finally, you need a game engine with an existing FK animation engine. You surely know HumanIK is not an animation engine. So this is all what we have, and this is what we want. Today we would like to be able to integrate HumanIK inside a game engine to do effector pinning. The purpose of effector pinning is to lock one or many parts of your character to a static or moving location in world space. This is useful when you want a character to climb on a wall, to grab an object on the ground, to grab a doorknob or whatever. This is how the integration process looks like. First step is prototyping. This is not a mandatory step, you can probably skip it, but it will make things harder to understand when things go wrong. This first step does not require any C++ knowledge. So let's talk about prototyping. Most of the IK behavior you would like to get in your final game, you should prototype it inside MotionBuilder. MotionBuilder is the best place to understand how the HumanIK solver works and how it blends IK with FK. If you are not able to obtain a correct IK solving inside MotionBuilder, you probably won't be able to get a proper solving inside your game code. The first thing to do is to make sure we use a relevant IK solver. When you get your HumanIK package, you get access to a HumanIK MotionBuilder plugin that matches your runtime build of HumanIK. You can have one or many solvers associated to a character in MotionBuilder. Now we should take a closer look to our animated character. This animation is coming from a motion capture source. The animation data is carried by the skeleton bones that are organized in a hierarchical structure. It is important to notice that it is not possible to immediately plug HumanIK on a character like this. HumanIK has no way of knowing that this hierarchy of bones represents a human body with 2 legs, 2 arms, a head and a spine. HumanIK needs you to describe your skeleton with a relevant semantic, and this is what we call the characterization process. During the characterization process, you need to specify to HumanIK which bone of the human body is implemented by your skeleton. Your character must be initialized in a basic T-stance that provides the HumanIK biomechanical model with crucial information about the geometry and proportions of the character's skeleton. The characterization process is a bit tedious. This is why we created this widget that is now available in most of our DCCs, the characterization tool. And this is how it works. One by one, you need to pick all important bones in your skeleton hierarchy and match them to HumanIK joints. Here, I'm selecting the hips on my character, then I'm matching this bone with the hips in the characterization tool widget. I'm doing the same operation for the upper leg, the lower leg, and the foot. I'm only going to characterize one spine bone here, but HumanIK supports up to 9 spine bones. Also, I'm characterizing the arm here. Please note that HumanIK automatically matches the symmetric nodes in the body if the naming convention you use is consistent. The more you give HumanIK knowledge about your skeleton structure, the better IK behavior you will get. HumanIK can also do IK on fingers and toes, and this is a great feature in some cases. I'm going to illustrate this in a minute. Here is an extract of the node HumanIK supports. There are some mandatory nodes displayed in red and some optional nodes displayed in black. As I told you, you can do IK on fingers and toes, and this can be useful. This is mostly used when dealing with birds or dragons. Here you see how finger bones are mapped to wing bones on a dragon. Thanks to the finger solving features of HumanIK, you will be able to do accurate IK on these wings. Please note, HumanIK is not only about humans. It works great with any biped and quadrupeds, and there are ways not out of the box, so to manage six-legged or more complex creatures. But let's get back to our human character. As soon as the characterization process is over, HumanIK is able to manipulate the skeleton. You know that the characterization is correct as soon as all bones in the characterization tool are displayed in green. In order to activate the solver, first you have to lock your characterization, and then you need to create a control rig. A control rig is a high-level controller for tweaking animations and blending FK and IK. See now that the solver is active. You can grab any effector on your character and move it around, and the character will move as expected. This is HumanIK in action. But what about our FK animation? If I move the current time on the transport control, the character does not move. And why is that? This is because the animation data is carried by the skeleton bones and not by the control rig. Currently the control rig is active, and since the rig itself is not animated, the character won't move. What we have to do is transfer the animation data from the skeleton to the rig, and this is what I'm doing right now. I'm plotting the animation to the control rig, and then both the FK and IK rig are animated and synchronized. So now when I move the current time on the transport control, the character is animated. Also, at any time, I can grab an effector and move it around, and this will trigger the full body IK solving. What I did to get there is I duplicated my character. This will be easier for us to make the difference between a character that is doing effector pinning and a character that is not doing effector pinning. I'm trying to replicate the setup of the game engine we will be integrating into. What I want to do here is to pin the left hand and the left foot of the character on the right on the gray cube and the gray platform on the ground. Right now both characters are playing the same FK animation. So in order to implement my IK behavior, I simply have to grab the character hand and to move it on the cube. This cube represents the target position and also a target orientation that the IK solver needs to reach. Now I'm doing the same for the foot. This should be good enough. This looks good, so what I'm doing now is I'm keying this pose. Remember, we are located at frame 0. Please note, if we move the current time on the transport control, the targets get lost. This is because we only keyed at frame 0, and other frames contain the keys resulting from the animation plotting on the control rig. Since I want my hand to stay pinned in these fixed positions, I'm just going to get rid of the keys on the wrist and on the foot. In order to do this, I'm using the F-curve control that is located here. Select, press delete. I do not need this data. Now when I move the current time on the transport control, it gets a bit better. At least the IK effector for the wrist and the foot that are represented in red, they stay at the right location. But what is wrong here is our blend factors between FK and IK. Right now the IK is not active on the wrist. So what I'm doing here is I'm putting full reach on both translation and rotation of the wrist. And now when I'm moving the current time on the transport controls, the arm tries to reach its target, but stops after reaching full extension. This is because the pull is not active yet. I'm going to activate it right now. And also for the foot. This looks much better. Let's say we are happy with this result, even if it can be improved a lot. And now try to get the exact same effect inside our game engine. Since we already did a lot of work inside MotionBuilder, we will be able to leverage this and export data files that will be loading in the runtime. In order to export this configuration data, simply select the solver attached to our character, go to the Properties panel and click on the following buttons. We are exporting three files: a character file containing the characterization data, an Effector file containing the Effector settings, and a Properties file containing all solver properties values. Now we are done with the prototyping and ready to write the initialization sequence in the runtime. So this is how our game engine looks like. It uses the Trinity Vision game engine. We have two characters animated by the Trinity animation engine. They are playing the same FK animation. We also have the cube and the platform on the ground that we want to use as targets for doing IK on the character on the right. These elements can be moved by the player with a keyboard. We want our IK to adapt to these target updates. In order to be able to start the solver of HumanIK, you need to initialize four objects. These four objects are listed here. The first object is an HIK character. You can build an HIK character from a valid characterization. The second object is an HIK character state. You can simply call it a pose. This object will be used to provide HumanIK with the current FK pose and to hold the final pose computed by the solver. The third object is an HIK Effector set state. This holds all the target positions and orientations to be reached by the IK solver. And finally, there is this HIK property set state object that allows you to tune the solver in many aspects. You can set up various parameters here that will affect the quality and the performance of the solving. In this integration example, we will stick to the default values. So let's start with the HIK character object. This object contains the characterization. Since we already characterized our character while prototyping inside MotionBuilder, we can simply load the binary characterization file in the runtime. The code for doing this is pretty trivial. You need to call this HIK load character function with the file name and the HumanIK license string. And that's all for the HIK character object. The three remaining objects should be created now, and we will update them each frame. To create these three objects, we will call three simple functions. These functions are HIK character state create, HIK effector set state create, and HIK property set state create. Also, what we do here is we initialize the HIK character state object with the default distance. This will be useful to check the validity of our integration. And finally, here we are synchronizing the IK or the FK with this last function call. And that's all for the initialization code. The main loop sequence is going to be a little bit harder to implement. If we run our game engine again, after writing the initialization code, nothing changed. There is only FK running on the characters. Here is what we need to do to activate the HumanIK solver. First, we need to provide it with a valid input FK character state, then we should call the solver, then we should write back the generated HIK character state on the game engine skeleton. This is the natural order for this sequence. But when doing an integration, I recommend you to begin with step 3, then continue with step 1, then finish with step 2. This is going to simplify a lot the error checking. First, we make sure we are able to write to game engine, then we make sure we are able to read from the game engine, and then we start the solver. So first, we should implement a way to write a character state back to our game engine. In order to do this, we need to call the HIK getNodeState function for each node in the character to retrieve its transformation in the HumanIK space. Then transpose this transformation in the game engine space, and finally send this information to the game engine animation system. And because we did not call the solver yet, and we did initialize our character state object with the t-stance, here is what you should see if you restart the game engine now. If the character on the right is not standing quiet on t-stance, there is an error in the integration code we just wrote. In our case, the result looks good, so we can start reading the input pose from the game engine. To provide HumanIK with the FK transformation for each node of your skeleton, please call the HIK setNodeState function. This takes 3 parameters, a translation, a rotation, and a scale value. Now if we restart the game engine, this is what we should see. The character on the right should play the exact same animation the character on the left is playing, but this animation data you see here is being properly read from your game engine, transferred to HumanIK structures, and properly written back to your game engine. Until this basic loop is not working perfectly, do not try to call the HumanIK solver. In order to finally activate the IK on this character, we need to properly set up the effectors for the left hand and the left foot. Remember, this is what we did 10 minutes ago when prototyping our IK in MotionBuilder. We had to position these effectors on the cube and the platform. We had to put full reach on both translation and rotation factors, and we had to increase the pool value to 1. We are now going to replicate the exact same operation in C++ code to get the exact same behavior in the final game engine. First, we need to set the position of the hand effector. In order to do this, we call the HIK setEffectorState TQSFV function, and we provide the desired position, translation, and scale value for the hand effector. This position is coming from the game engine and matches the cube position. Then, we set the reach value for translation and rotation to 1, as well as the pull value. We do the same for the foot effector, and finally we are able to call the HumanIK solver that is taking as an input the 4 data structures that we described before. The resulting pose will be stored in the character state object we passed in that contains the input FK pose. So now, if we run the game engine again, here is what we see. The IK works as expected, and we are able to move the pinning position for both the hand and the foot of the character. Please note how easily we did this. We just had to know about 10 functions of the HumanIK API to write this example.